Come on, open up. What's wrong? Sounds like you're making trouble. No? Alright. Okay, fission and fusion. Got this? Yeah. Okay, so we'll have a look at some applications here. So in this example here, in fact you did the formula for me in the exercise. What you have here is 1 neutron is fired at uranium-235. That's actually question 2 in your questions, isn't it? Yeah. Do you see it there? Question 2. And what does it make? Well, it will then become krypton and barium. And then you have 3 neutrons, and then you have some energy. And in fact, I asked you to work out how much energy. What was the answer you got to? Or Abraham, if you got it?
2.7
and those you got to? Did you get part 2 done, Louise? No. 2A. Yeah. The energy.
The energy is 3.7.
Oh, guys, okay. Anyway, this here is actually called nuclear fission. What you're doing is you have something like uranium and you break it by firing a neutron at it. So the neutron comes in, hits the atom, and the atom breaks into 2 pieces. It becomes krypton 92, barium 141, and 3 neutrons break free. And you have calculated how much energy you have here. And this is actually nuclear fission. So the definition would be nuclear fission is the splitting. You know what I mean by split? Breaking 2? Is the splitting of heavy atoms to create energy. So, can you please write that definition down? Nuclear fission, let's try this again, N-U-C-L-E-A-R, nuclear fission is the splitting, yeah, good. This is okay. The splitting of heavy, yes, Y at the end, heavy atoms into lighter atoms. And releasing energy. Yes. Good job. So this is how you can make energy by this process. Now, if you look back here, you see that you get 3 neutrons that come out. So what you could do is you could then use these neutrons to break more uranium atoms. So, you see here I have a picture. The idea is the uranium breaks and releases 2 or 3 neutrons, and then these neutrons hit more uranium and they break and release more neutrons, and then these neutrons hit more uranium. You see what's happening here? A chain reaction, yeah. So what's happening here is each time the neutrons are released after they split more uranium. And this is called a chain reaction. So how would we define chain reaction? Who wants to try? Abraham, you want to try, yeah?
Chain reaction is from 1 neutron, it's uranium.
Yep.
And then more neutron is released, more neutron.
Yes, Yes, I understand that. Release more neutrons. Yes. Now we want maybe some nice words here that can help us explain this. So we have the idea that when don't write just yet. So we have the idea that when the neutrons come out, they break more uranium, which frees more neutrons. So I suppose you could say the release of neutrons causes a further release of neutrons, which then causes a further release of neutrons. This is a chain reaction. That's the simplest way I can put it. It's like that game, the dominoes. You know dominoes? You knock one domino down and then they all fall. It's like this. So you could say, if you want to write the definition down, a chain reaction. A chain reaction is when neutrons released from uranium. So a chain reaction is when neutrons released from uranium splitting or uranium breaking, whatever you want to call it. Splitting is fine. So neutrons released from uranium splitting cause further uranium to split. F-U-R-T-H-E-R. So what we got so far? Chain reaction is when neutrons released from splitting uranium cause what we got so far? Cause further uranium splitting, which releases more neutrons. Yeah. So let's see what you got here. Chain reaction is when neutrons released from uranium splitting cause further uranium splitting, which releases more neutrons. So it continues on like this. Okay. Next. So in fact, you can use this to make power, electricity in the power plant. So what happens here is you have cold water that comes in and it goes into this tank here. And then you see here, beside the tank is the reactor core. Now, in the, you see the red? You see the red? That's uranium. And this uranium, there's a chain reaction, so it's releasing lots of energy. And when you have lots of energy, it'll get very hot. So then it makes the water hot, turns it into steam, and then the steam turns a wheel that makes the electricity. There are, let me see, the moderator's missing from this diagram. But anyway, there's something I want to show you there. You see where it says control rod? So what you do is, when you want lots of energy, you put the control rod up. And then when you want no energy, you put the control rod down. And the control rod is like, covers the uranium. You know, it's like a lid. You know what I mean? Like, here's the uranium, and then here's the control rod. So this has lots of energy because there's lots of energy coming off of it. Makes it very hot. And then when you want less energy, you just cover it up. And then when you want no energy, you push it down all the way. So the control rod is like how much energy you want. You want lots of energy, you lift it up, and you want no energy, you push it down. That's the control rod. So you don't need to draw this, but it's good to understand how it works. So the uranium, there's a chain reaction going on, so there's lots of energy coming off of the uranium fuel, and then this makes heat, and the heat makes steam in the water, and so on. What you do need for the exam is to explain, come on, fuel rod. Hang on, let me just check something here. Yeah, it's not on my diagram here, but here you have the fuel rod, and there's another material here called a moderator. Moderator is like a shield. We'll get to that in a moment. Anyway, let's talk about the fuel rod. So nuclear fuel is a material that can be burnt by nuclear fission or fusion, and most commonly it's uranium or plutonium. So for this power plant, the fuel that they use is uranium-235 or plutonium-239. That's what's used. So it's called fuel rod because it looks like a rod. You know what a rod is? Like a stick. Yeah. And I think most would be uranium, anyways. So what you just need to know for the exam is uranium fuel rod is a fuel rod is basically uranium-235 or plutonium-239. That's basically it. Now there's other stuff in it as well, but it's uranium or plutonium, really, that's all it is. So can you just make note that a fuel rod is used in power plants, and it's normally uranium-235 or plutonium-239. In power plants, nuclear power plants if you want. Nuclear fuel is used in power plants. It is normally uranium-235 or plutonium-239. Now, it's not actually just uranium-235. It's actually a mixture of different isotopes of uranium. I think the uranium-235 is actually only 2% of it. There's other isotopes of uranium in it. It's just the uranium-235 is very unstable. This is why it's only 2%. But the uranium-235 is what makes it powerful. It's like you make it more unstable by adding 2% of this. Very dangerous. That's why it's only 2%. It's quite very unstable. Very unstable. Okay. Now, it's not really important, but where do you get this uranium from? Well, first you mine it, then you refine it, then you purify it. So there's a long process here. Yeah, what's wrong? Where does uranium-235 come from? Yeah, where would you find uranium? Where does it come from? Any of this? I think Australia has lots of uranium mines. You take it from the earth. Yeah, I think Australia. Yeah? Alright. Huh?
It's in wine.
Why?
Yeah.
Why what?
Wine in Australia.
Why is oil in the Middle East? That's where it is. Okay. Now, moderator. This was not on my diagram, but the moderator is around the reactor, and basically it's like protection. It can absorb the neutrons, so it's like a shield. So you can just say moderator is the shield of the reactor. Yeah. You know shield?
No.
Shield, like protection, barrier. You know barrier? Protection. You know protection?
Yes, I
It's a very common one.
Yes, magic barrier. Yeah. So shield just means like protection, a barrier. Because it's very dangerous, so you need something to protect you. And what we normally use, does it say there? Yeah, water or graphite. I don't think I said it there, or maybe I said it next. No, I didn't. Anyway, graphite, yeah. Graphite is what you have in your pencils. So amazingly, this is what's used to protect you. You know, in your pencil? You got a pencil? Yeah. He did this in chemistry. This is graphite here. This is used in the reactor here. Like here. Like you see here? This is made of graphite. It's called the moderator. And as I said, it's usually graphite, but there's other materials as well you can use, like water and crap. But graphite. So moderator is normally graphite and it protects or shields the reactor. So what have you got? Moderator is the shield of the reactor. It is normally graphite. Yeah? Moderator is the protection used in a power plant. If you want to write that in, used. Yeah. Yes. In the power plant. Yeah. Power plant. Power station. You know? Yeah. Yeah, I'll help you. You know what I mean here? Power plant. You know power plant? Where the power is from. Yeah, the picture there, yeah. The moderator is the protection used in the power plant. It is normally graphite. Graphite is in your pencil. Yeah, you got that? What did you write, Abraham? Yes, yeah. Graphite is graphite or water. Yeah. Okay. So we have fuel rod, we have moderator, we have control rod. So if you remember, I was talking about the control rods, which cover the uranium. So what's the job of the control rod? It's to adjust or change the energy levels. You know, like a switch, more or less energy. And what are they made of? They're made of something like boron or silver or indium or cadmium. They're made of materials like this. So you can just say control rod can reduce the energy output. Control rod can reduce the energy output. It is normally, I think, boron is quite common. As you can see, I don't know, silver might be too expensive to use. Boron. Yeah, boron. B-O-R-O-N. Yeah, what did you write, Louise? Control rod, yeah, can reduce the energy output is boron, yeah. Control rod, yeah. Got that? Yeah. Okay. Now, the last one here, at the start we started with fusion. So with fusion, what do you have? You have like uranium, and then you have like a neutron, and the neutron comes in and hits the uranium, and the uranium then breaks, into two other elements, and then 3 neutrons come out. So then at the other side you have 3 neutrons coming out, and these can break more uranium, make more and more energy. Yes?
The fusion or fission?
This one is fission. Oh, sorry, that one should say fusion at the top. Yeah. So this one is fusion. Well, you can see here in the picture now. Fusion. So what we did was fission. I did say fission, didn't I? I hope I didn't say fusion. Oh, thank goodness. Alright, so fission is the first one. This one here is fusion. Yeah, that shouldn't say fission, it should say fusion. So fusion is the opposite nearly. So what you do is you take 2 elements, you know what I mean? It's like backwards. You take 2 elements and you stick them together. So in the fission, you have a neutron and it breaks this into 2 elements. In the fusion, you have 2 elements and they come together to make something new. So it's the opposite nearly. So here's my example. You see here, you have deuterium, which is a proton and a neutron, so that's hydrogen. And you have tritinium, which is 1 proton and 2 neutrons, so that's also hydrogen. And these 2 hydrogen atoms come together, and then they form helium and a neutron. But if you calculate the mass is less, so it's actually made some energy. This is what happens in the sun. The sun is made of hydrogen and helium. So what happens is you have your hydrogen, it comes together and it turns into helium and energy. Yeah? Now what do you think makes the hydrogen come together? What pushes the hydrogen together to make helium and energy? Yes, of course. What force? What force? No. Here, let me give you a clue. Gravity. So gravity takes the hydrogen and pushes it together. And what does it become? Helium and energy. And we feel the energy. It's what comes to us.
And the nucleus
You know, it's not actually, you know, it would be so nice if it was, because that would be a nice simple answer, but in fact it is not. It is not. The neutrons just stay in the sun. Now, I've made this very simple. Lots of other things happen too, but basically the hydrogen comes together, makes helium and energy. So this is called nuclear fusion. So before you write it down, what would you say is the definition of fusion?
Nuclear fission is a combination of
Yeah.
deuterium.
Well, not just these. It can be any 2 atoms, really. This is just my example, yeah.
Combination of atoms to form energy.
Yeah, and it doesn't even have to be helium, it can just be another atom, yeah. So, fusion is the force combining of atoms to make a new atom and energy. So, fusion is this word is important, force, because you really have to push them together. It's not easy to do. So forced, and maybe you want to underline forced. It's the forced combining of light atoms. It's the forced combining of light atoms into heavier atoms and energy. So, let's see. Fusion is, the forced combining of 2 atoms, 2 light atoms, into a heavy atom and energy. Okay, what did you write, Abraham? Fusion is the forced combination of light atoms into heavier atoms and energy. Good. you actually have the example there. Fusion is the forced combining of two light atoms into heavier atoms at energy. Yeah. So all our nuclear power plants actually use fission. But there is plans to make fusion power plants. This is a very difficult process, in fact. Very difficult. The reason fission is more common because number one, it's easier to do. Number two, it's cheaper to do. Fusion is very difficult to do and very expensive to do. So this is it's a simple money reason. Okay?
Which way is more better?
Unfortunately, the one we use now. This here is very, very, very safe. The previous one with the uranium is very, very unsafe. So unfortunately, the one which is unsafe is the one that is cheap and what we use. And the one which is safe is expensive and we don't use it. And you know that's unsafe because you've seen what happened in Japan and in Russia and other places too. So in maybe 10 years, maybe 20 years, more countries will use this reaction instead of the uranium reaction we saw at the start. Yeah. I think there are some plans to make power plants that use fusion, but I still think it's at least 10 years before it happens. It's a difficult process. It's a difficult process, yeah. The reason it works in the sun is because the sun is so big and has so much force. It's very easy for it to push the hydrogen together. But for people on Earth, pushing hydrogen together is quite a difficult thing to do. So it's not difficult for the sun to do, it's difficult for us to do. So we're so much smaller. Yeah. Okay, I'll find out today what the story is with ETAP exam tomorrow, okay? But I think maybe there might be a problem with the physics class.